Hello there and welcome to the Snoozy Explorer channel. Tonight we are descending into a hidden world that exists directly beneath your feet. A realm where cities grow downward instead of upward, where darkness becomes workspace, and where human ingenuity has learned to carve paths through the impossible. This is the quiet frontier of underground construction. It is a place where geology meets ambition, where patience measures itself in inches per day, and where the greatest structures are the ones nobody sees. This is a world of pressure, precision, and careful listening to what the Earth itself is trying to say. As we explore this buried dimension, we will discover the delicate dance between human planning and geological surprise, where every tunnel tells a story of persistence written in stone and steel. If you enjoy these gentle journeys beneath the surface of everyday life, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy explorer at a time. But for now, all you need to do is relax. Allow your body to settle deeper into comfort and your thoughts to drift downward with us. Let your breathing slow as we begin our descent. Let's begin. Every tunnel starts not with digging but with looking. Before a single shovel touches earth or a machine begins to turn, engineers must understand what lies beneath. The ground under cities is not uniform. It is layered, fractured, and full of surprises. Some layers are soft clay that yields easily. Others are hard rock that resists every attempt to break through. Between these layers, water flows through ancient channels, following paths that were established long before any city existed above. What makes this so fascinating is that you cannot see what you are about to dig through. The Earth keeps its secrets. Engineers send down core samples, drilling narrow holes hundreds of feet deep and pulling up cylinders of soil and rock. Each sample is like a chapter in a book, telling the story of what formed there over millions of years. Compressed sediment from ancient seas, volcanic rock pushed up from below, gravel deposited by rivers that changed course long ago. Reading these samples becomes an art as much as a science. The ground also contains the infrastructure of the city itself. Gas lines run beneath streets, some installed a century ago with maps that no longer exist. Water mains branch in unexpected directions. Electrical conduits snake through the subsurface in patterns that made sense decades ago but now seem chaotic. Storm drains and sewer systems occupy their own territories, built in different eras by different crews with different standards. Before tunneling can begin, engineers must locate every single one of these hidden arteries. They use ground-penetrating radar that sends pulses into the earth and listens for echoes. They study old municipal records, some handwritten in ledgers that predate computers. They interview longtime city workers who remember where things were placed. This detective work can take months or even years, but it is essential. Cutting through a gas line or flooding a tunnel by breaking into a water main can be catastrophic. What makes this preparation so compelling is the patience it requires. There is no rushing this phase. The Earth will only reveal itself slowly through careful questioning. Engineers must accept uncertainty even after all their research because the ground can still surprise them. An unexpected pocket of soft soil. A boulder where none should exist. An underground stream that the surveys missed. The tunnel has not yet begun, but already the project is teaching humility. The ground beneath cities is not empty space waiting to be carved. It is a crowded, complex environment where human additions have layered atop geological history for generations. Understanding this landscape becomes the foundation for everything that follows. Cities also move above while tunnels are built below. Traffic cannot stop. Buildings cannot be abandoned. People need to reach work, schools, and homes without interruption. This means that tunneling must often happen with minimal surface disruption. The challenge is to burrow deep beneath streets and structures without causing the ground above to shift or settle. Even a small amount of settling can crack building foundations, damage roads, or break utility lines. Engineers design tunnels with this constraint always in mind. They calculate how much stress the surrounding earth can handle. They predict how soil will behave when a void is carved through it. They plan routes that avoid the most sensitive areas, sometimes adding extra distance to the tunnel just to stay away from a historic building or a major intersection. The act of not disturbing what exists above becomes as important as the tunnel itself. Monitoring equipment is installed throughout the neighborhood, measuring tiny changes in ground level. Sensors placed on building walls detect movement measured in fractions of an inch. If anything begins to shift, work can be adjusted immediately. What makes this so remarkable is the precision involved. Tunneling is often imagined as rough, forceful work. In reality, beneath cities, it becomes almost surgical. Every movement is calculated. Every bit of removed earth is accounted for. The goal is invisibility, to create a massive underground structure while the city above continues its daily rhythm without noticing the transformation happening below. Tunnel boring machines have revolutionized how tunnels are built under cities. These machines are marvels of engineering, massive cylindrical structures that can be longer than a football field and weigh thousands of tons. At the front is a circular cutting head covered with disc cutters or teeth, designed to grind through whatever geology stands in the way. Behind this cutting head is a long trailing section that houses control rooms, conveyor systems, and support equipment. The entire machine moves forward as it cuts, creating the tunnel as it advances. What makes these machines so captivating is their self-contained nature. They are like underground factories, complete with lighting, ventilation, and workspaces for crews. The machine eats rock and soil at one end and leaves behind a finished tunnel at the other. The cutting head rotates slowly but with tremendous force. In soft soil, the cutters might complete several rotations per minute, carving smoothly through clay and sand. In hard rock, progress can slow to inches per hour as the cutters strain against stone that has been compressed for millions of years. The machine pushes itself forward using hydraulic jacks that press against the tunnel walls it has just created. This constant cycle of cutting, advancing, and bracing continues 24 hours a day, 7 days a week. Stopping a tunnel boring machine is costly and complicated, so once tunneling begins, the machine rarely rests. Crews work in shifts, keeping the operation continuous. What makes this so mesmerizing is the relentlessness. Day after day, the machine advances through total darkness, guided by lasers and navigation systems, carving a path that must align precisely with survey points on the surface. The removed material, called muck, is transported out of the tunnel on conveyor belts or in rail cars. This material must go somewhere, and the volume is staggering. A single tunnel can generate hundreds of thousands of tons of excavated earth and rock. In some projects, this material is transported to landfills or used to create new land in waterfront areas. In others, it is processed and recycled for construction projects elsewhere in the city. The logistics of removing this much material without overwhelming surface streets requires careful planning. Trucks may only be allowed to operate during certain hours. Routes must be planned to avoid residential neighborhoods. Staging areas must be large enough to handle the constant flow without creating bottlenecks. The tunnel itself becomes only part of a larger system that extends to the surface and beyond. Tunnel boring machines must also manage water. Groundwater is present almost everywhere beneath cities, flowing through porous layers or collecting in underground reservoirs. When a tunnel intersects these water sources, the machine must prevent flooding while continuing to advance. Some machines operate in closed mode, where the cutting head is sealed and the excavation chamber is kept pressurized. This pressure balances the water pressure outside, preventing water from rushing in. Material is removed through a system of airlocks and slurry pumps. Other machines operate in open mode in drier conditions, but still must pump out water that seeps in through the tunnel face. Managing water becomes a constant concern. Too much water can destabilize the tunnel face, causing collapses. Too little attention to drainage can flood the workspace. The machine must find a balance, adjusting its operation to match the geology it encounters. What makes these machines so fascinating is how they adapt. Modern tunnel boring machines are equipped with sensors that constantly measure ground conditions, water pressure, and machine performance. Operators in the control cabin receive real-time data and can adjust cutting speed, pressure, and advance rate accordingly. The machine becomes responsive, almost intelligent, reacting to what it encounters rather than pushing blindly forward. This adaptability is crucial because no two stretches of tunnel are identical. The ground changes. Unexpected obstacles appear. The machine must respond to each new challenge while maintaining progress toward a destination it cannot see, guided only by coordinates and the steady accumulation of distance. Before tunnel boring machines existed, tunnels were built by hand. Miners would drill holes into the rock face, pack them with explosives, and blast away sections of stone. After each blast, workers would enter the newly created space, clear the debris, and repeat the process. This method, called drill and blast, is still used in certain conditions, particularly in hard rock where tunnel boring machines would struggle. What makes this method so striking is its directness. Instead of gradual grinding, progress happens in sudden, violent bursts. A blast can remove several feet of rock in seconds, but then hours of work follow as crews stabilize the walls, remove rubble, and prepare for the next blast. The rhythm is entirely different from the steady advance of a boring machine. It is punctuated, deliberate, and requires workers to constantly enter freshly blasted spaces where the rock may still be unstable. Drill and blast tunneling requires extraordinary skill. Drilling holes in precisely the right pattern determines how cleanly the rock will break. If holes are placed poorly, the blast can create rough surfaces, leave unstable overhangs, or fail to remove enough material. Experienced crews develop an intuition for how rock will fracture, reading the geology and adjusting their drilling patterns accordingly. The explosives themselves must be carefully measured. Too much force can damage surrounding rock, creating cracks that weaken the tunnel. Too little leaves behind rock that must be removed manually. What makes this work so compelling is the craftsmanship involved. Each blast is a small sculpture, shaping rock through controlled destruction. The goal is not just to remove material but to leave behind walls that are stable and smooth enough to support the tunnel structure. After blasting, the newly exposed rock must be stabilized immediately. In some cases, this means installing rock bolts, long steel rods drilled deep into the surrounding stone to hold loose sections in place. In other cases, wire mesh is draped over the walls and anchored, preventing small rocks from falling. Sometimes the entire surface is covered with shotcrete, a type of concrete sprayed under high pressure that adheres to rock and forms a protective shell. This stabilization work happens quickly because unstable rock is most dangerous in the first hours after blasting, before stresses have redistributed. Crews work in dim light, surrounded by dust and the smell of explosives, feeling the rock for loose sections and listening for subtle sounds that might indicate instability. What makes this so remarkable is the trust required. Workers must enter a space that has just been violently disrupted and make it safe through their own hands and judgment. The decision to use a tunnel boring machine or drill and blast depends on many factors. Geology is primary. Soft ground favors boring machines. Very hard, fractured rock might favor blasting. The length of the tunnel matters too. Tunnel boring machines require significant time and expense to assemble and launch, but once operating, they advance steadily. For short tunnels, this setup time might not be worth it. For long tunnels, the machine's consistency makes it invaluable. The urban environment also influences the choice. Blasting creates vibration that can damage nearby structures. In densely built areas, this makes blasting risky or impossible. Tunnel boring machines create less vibration and can operate with minimal surface impact. What makes these decisions so fascinating is that there is rarely one obvious answer. Engineers must weigh dozens of factors, balancing cost, time, risk, and capability. The method chosen shapes everything that follows. Tunnels must be lined to prevent collapse and create a stable interior. As a tunnel advances, the walls and ceiling are raw earth or rock, shaped but not yet secure for long-term use. Lining the tunnel transforms this temporary excavation into a permanent structure. In soft ground, precast concrete segments are often used. These segments are curved pieces that fit together like a jigsaw puzzle, forming a complete ring. As the tunnel boring machine advances, a mechanical arm called an erector lifts these segments into position and bolts them together. Each ring is installed immediately behind the machine, so the tunnel is lined as it is created. What makes this so elegant is the continuity. The machine never leaves behind an unprotected section. The tunnel emerges from the machine already encased in its permanent structure. These concrete segments are manufactured to extraordinary precision. They must fit together perfectly, leaving minimal gaps, because any space between segments can allow water to seep in or create weak points. The segments are curved to exact specifications, often with tolerances measured in millimeters across pieces that weigh several tons. Gaskets are embedded in the edges to seal joints against water. Bolt holes are precisely located so segments align correctly. Manufacturing these segments is a project within the project, requiring dedicated facilities and quality control that ensures every piece will perform correctly hundreds of feet underground. What makes this so compelling is the marriage of mass production and precision. Thousands of segments are made, each one nearly identical, yet each one must be perfect because failure of a single segment can compromise the entire tunnel. In rock tunnels built by drill and blast, lining may be simpler. If the rock is strong and stable, a layer of shotcrete may be sufficient, sprayed directly onto the rock surface to seal it and prevent erosion. In some cases, a more elaborate lining is installed afterward, with steel reinforcement and poured concrete creating a smooth interior. The choice depends on the rock quality and the tunnel's intended use. A tunnel that will carry trains needs a smooth, durable interior. A utility tunnel accessed only for maintenance may require less finish. What makes this decision process so interesting is that it balances engineering requirements with practicality. Over-engineering adds cost and time. Under-engineering creates risk. Finding the right level of protection requires understanding not just what the tunnel needs today, but what it will face over decades of use. Water management is one of the most constant challenges in tunnel construction. Groundwater does not respect human boundaries. It flows according to pressure gradients, seeking the lowest points and following paths of least resistance. A tunnel carves through these flow patterns, creating a void that water wants to fill. Managing this water requires multiple strategies working together. Sometimes water is allowed to seep into the tunnel but is collected in drainage systems and pumped out continuously. Other times, the tunnel is made watertight, with sealed joints and waterproof membranes preventing water from entering at all. The choice depends on the water volume, the tunnel's use, and the surrounding geology. In some projects, engineers lower the groundwater table before tunneling begins. Wells are drilled around the tunnel route, pumping water out and temporarily lowering the water level. This dewatering can make excavation easier and safer, but it comes with its own challenges. Lowering groundwater can cause the surface to settle as water is removed from soil pores. Buildings can be affected. Nearby wells can run dry. Careful monitoring is essential to ensure that solving one problem does not create others. What makes this so delicate is the interconnectedness. The water beneath a city is part of a larger system. Changing it in one place affects conditions elsewhere. Engineers must think beyond the immediate tunnel, considering how their actions ripple through the underground environment. Once water is managed during construction, the tunnel must continue managing it throughout its life. Drainage systems are built into the tunnel floor, collecting any seepage and directing it to pumping stations. In some tunnels, you can hear water trickling constantly, a quiet reminder that the surrounding earth is always pressing inward, always seeking to reclaim the space. Pumps run continuously, removing water before it can accumulate. Maintenance crews inspect drains regularly, clearing blockages and ensuring flow paths remain open. What makes this ongoing work so essential is that water is patient. It never stops. A tunnel that is dry today can flood within hours if pumps fail or drains become clogged. The battle against water is never won, only managed through constant vigilance. Ventilation is critical in tunnel construction and use. Underground, air does not circulate naturally. Without ventilation, the tunnel becomes a trap for dust, exhaust fumes, and dangerous gases. During construction, fresh air must be pumped in continuously, both for workers to breathe and to clear the air of particles created by cutting or blasting. Large fans and ducting systems push air through the tunnel, creating a flow from the entrance to the working face and back out. This system must move enormous volumes of air to keep conditions safe. In long tunnels, the ventilation system itself becomes a major component of the project, requiring its own power supply, maintenance, and monitoring. The type of work being done affects ventilation needs. Drill and blast operations generate huge amounts of dust and smoke from explosives. After each blast, the tunnel must be cleared completely before workers can safely enter. This can take an hour or more, with fans running at full capacity to push contaminated air out. Tunnel boring machines generate less dust but still require ventilation to remove exhaust from equipment and to provide fresh air for crews working in the confined space. What makes this so important is invisibility. You cannot see bad air. Carbon dioxide can accumulate silently. Methane can seep from certain rock formations. Diesel exhaust can build up to dangerous levels. Monitoring systems measure air quality constantly, alerting crews if conditions deteriorate. Ventilation becomes the invisible safety net that makes underground work survivable. Once a tunnel is complete, ventilation remains essential. Tunnels that carry vehicles must remove exhaust continuously. Even pedestrian tunnels need air circulation to prevent stuffiness and ensure comfort. Large ventilation shafts are built at intervals, connecting the tunnel to the surface. Fans in these shafts can push air in or pull it out, creating a steady flow. In emergency situations, such as a fire, the ventilation system can be reversed or adjusted to push smoke away from evacuation routes. What makes these systems so fascinating is their scale. Moving enough air to ventilate a mile-long tunnel requires fans as large as those in industrial wind tunnels, consuming enormous amounts of electricity and requiring careful engineering to operate quietly enough not to disturb surface neighborhoods. This work so demanding is that every challenge is magnified by depth. A problem at the bottom of a 300-foot shaft is much harder to address than the same problem at ground level. Once a tunnel is built, it must be equipped for its purpose. A transit tunnel receives tracks, signals, electrical systems, lighting, and communication equipment. A road tunnel gets pavement, lighting, ventilation controls, and emergency systems. A utility tunnel is fitted with racks, supports, and access points for the pipes and cables it will carry. This outfitting phase transforms a raw excavation into a functional piece of infrastructure. What makes this phase so intricate is the coordination required. Multiple contractors work simultaneously, installing different systems that must all fit within the tunnel's limited space and must all work together. Electrical systems must not interfere with communication systems. Ventilation ducts must route around lighting fixtures. Every element must be installed in the correct sequence because some work cannot proceed until other work is complete. Testing is exhaustive before a tunnel opens. Every system is checked and rechecked. Ventilation fans are run for hours to ensure they move sufficient air. Emergency lighting is tested to confirm it provides adequate illumination if main power fails. Communication systems are verified throughout the tunnel's length. In transit tunnels, trains run empty through the tunnel repeatedly, testing track alignment, signal timing, and vehicle clearance. Water drainage systems are flooded intentionally to ensure they handle design volumes. What makes this testing so critical is that once the tunnel opens, there may be no easy way to fix problems. Shutting down a tunnel for repairs disrupts the entire system it was built to serve. Better to find and fix issues during testing, even if it delays opening, than to open with hidden flaws. The geology of cities shapes where tunnels can go and how they are built. Cities built on bedrock, like Manhattan or Stockholm, have solid foundations that make tunneling through rock necessary but predictable. Cities built on sediment, like New Orleans or Venice, face challenges with soft, waterlogged ground that can be difficult to tunnel through and prone to settling. Cities on mixed geology, where rock and soil layers alternate, must deal with constantly changing conditions as tunnels pass from one material to another. What makes this so fascinating is that cities cannot choose their geology. They must work with what exists. This geological constraint shapes the city's infrastructure in profound ways, determining where subways can run, how deep tunnels must go, and what methods are feasible. In some cities, ancient tunnels and structures complicate modern construction. Rome, for example, sits atop layers of history, with ancient aqueducts, catacombs, and building foundations scattered beneath the modern surface. Any new tunnel risks intersecting these archaeological remains, which must be documented and often preserved. This adds time and complexity to projects. Crews may encounter a Roman wall or an ancient tomb and must stop while archaeologists examine the find. What makes this so poignant is the layering of human effort across time. Modern engineers carving paths through earth disturbed by engineers 2,000 years ago, both responding to the same human need to move, connect, and build. Tunnels change the cities above them. A new subway line reshapes neighborhoods, making areas more accessible and often more valuable. People move differently. Businesses open in places that were previously isolated. The city's center of gravity can shift as new connections are made. What makes this transformation so gradual is that it unfolds over years. A tunnel opens and immediately there is convenience, but the deeper changes take time. Property values adjust. Traffic patterns shift. The city reorganizes itself around the new infrastructure. Planners try to predict these changes, but cities are complex systems that often respond in unexpected ways. The tunnel becomes a catalyst, setting changes in motion that ripple outward in ways that are only fully understood decades later. Building tunnels beneath cities requires public patience. Construction can last years, during which streets may be closed, noise may disrupt neighborhoods, and inconvenience is constant. Yet the benefit is mostly invisible and lies in the future. Residents must tolerate disruption now for a tunnel they may not see or use until years later. What makes this social contract so delicate is trust. The public must trust that the disruption is worth it, that the project will be completed as promised, and that the benefits will materialize. When trust breaks down, opposition grows. Projects face delays, lawsuits, and political challenges. Successful tunnel projects manage public relations as carefully as they manage engineering, communicating progress, acknowledging difficulties, and demonstrating that the work is proceeding responsibly. The cost of urban tunneling is staggering. Tunnels can cost hundreds of millions or even billions of dollars per mile, depending on depth, geology, and complexity. This expense comes from the specialized equipment, the skilled labor, the long construction times, and the need to work around existing infrastructure without disrupting the city. What makes these costs so challenging politically is that they are hard to justify in simple terms. A tunnel produces no immediate revenue. Its value is in mobility, in reduced congestion, in future capacity. These benefits are real but diffuse, felt by many people in small ways rather than by a few people dramatically. Funding such projects requires long-term thinking and willingness to invest in infrastructure that pays dividends over decades. Despite the cost, cities around the world continue building tunnels because the alternative is worse. As cities grow denser, surface space becomes impossibly crowded. Streets cannot be widened indefinitely. Buildings cannot be moved. The only direction left is down. Tunnels allow cities to expand their capacity without expanding their footprint. What makes this so essential is sustainability. Dense cities with good public transit are more efficient, producing less pollution per person and consuming less energy. Tunnels make that density livable by providing transportation options that do not clog streets. The investment in tunneling is an investment in the city's ability to function as it grows. Safety is paramount in tunnel construction. The work is inherently dangerous. Crews work underground, surrounded by tons of earth held back only by engineering and careful practice. Cave-ins, though rare, can be catastrophic. Equipment malfunctions can injure workers. Fires in confined spaces are particularly dangerous because smoke has nowhere to go. What makes tunnel construction safer than it once was its obsessive attention to procedures, training, and equipment. Workers wear protective gear constantly. Air quality is monitored continuously. Escape routes are clearly marked and kept clear. Drills practice emergency responses so that if something goes wrong, everyone knows what to do without hesitation. Historically, tunnel construction was far more dangerous. In the 19th and early 20th centuries, workers died in large numbers building tunnels. Cave-ins were common. Ventilation was poor, leading to suffocation or long-term lung damage. Explosives were handled carelessly. Workers had little protection and no recourse if injured. What makes modern tunneling so different is the value placed on worker safety. Regulations require safe conditions. Unions advocate for protections. Companies understand that accidents delay projects and damage reputations. The change is not just technological but cultural, a recognition that progress is not worth lives and that safe work is possible with proper care. Even with all precautions, accidents still happen. A tunnel in Seattle had to stop for years when the tunnel boring machine hit an obstruction and was damaged. A tunnel in Germany flooded when unexpected groundwater broke through. A tunnel in China collapsed during construction, trapping workers who were rescued only after days of effort. What makes these incidents so sobering is the reminder that underground work pushes the limits of what humans can control. The Earth is powerful and unpredictable. Respect for that power is essential. Tunneling is not an act of conquest but of negotiation, finding a path through the Earth by understanding its properties and responding to its challenges with care rather than force. The people who build tunnels develop a unique relationship with the underground. They work in darkness most of the time, their world reduced to the illuminated area around the tunnel face. They feel the Earth differently than people on the surface, aware of its weight, its moisture, its temperature. They learn to read the subtle signs that indicate stable or unstable ground, sounds that suggest water approaching, vibrations that mean equipment needs adjustment. What makes this expertise so valuable is that it cannot be fully taught. It comes from experience, from time spent underground, from mistakes and close calls and successes that build an intuitive understanding of how Earth behaves. Tunnel crews often develop strong bonds. The work requires trust. Everyone depends on everyone else to do their job correctly because mistakes can endanger the whole crew. This interdependence creates camaraderie. Workers look out for each other, share knowledge, and take pride in their collective achievement. When the tunnel is complete, many crew members feel a mixture of satisfaction and loss. The project that consumed months or years of their lives is done. They move on to the next tunnel, the next city, the next challenge, carrying with them the memory of passages carved through stone and earth that most people will never see but thousands will use. The tunnels themselves become part of the city's hidden anatomy. Most people using a subway tunnel never think about how it was built. They board a train, travel underground, and emerge elsewhere. The tunnel's simply a convenient void that connects places. What makes this invisibility so interesting is that it represents success. A tunnel that draws attention is usually a tunnel with problems. A successful tunnel disappears into the background of daily life, noticed only in its absence if it closes for repairs. The effort, expense, and ingenuity that created it become invisible, taken for granted, which is exactly as it should be. Infrastructure works best when it is not noticed. Yet for those who built it, the tunnel is never invisible. Engineers who designed it can point to solutions they devised for specific challenges. Workers who excavated it remember long shifts underground, the smell of diesel and dust, the satisfaction of progress measured in feet per day. Geologists who interpreted core samples see the tunnel as a path through layers they studied in detail. For them, the tunnel is a story of problems solved, a testament to collaboration between people and machines and careful planning. What makes this dual existence so poignant is that the tunnel is both utterly ordinary to most and deeply meaningful to a few. Some of the world's longest tunnels took decades to complete. The Gotthard Base Tunnel in Switzerland, running 35 miles through the Alps, took 17 years to build. The Channel Tunnel connecting England and France took 6 years of intense work after years of planning. These projects represent massive commitments of resources and patience. What makes them so impressive is not just their length but their persistence through difficulties. Unexpected geology, funding challenges, political changes, all had to be navigated while keeping the project moving forward. The tunnels stand as monuments to human determination, to the willingness to start something that will not be finished for years, trusting that future effort will complete what present effort begins. Shorter tunnels can be equally challenging if conditions are difficult. A half-mile tunnel through fractured rock beneath a densely built neighborhood might take as long as a much longer tunnel in stable ground with open space above. What matters is not just distance but context. Every tunnel is unique, shaped by its specific geology, its urban environment, and its purpose. Comparing tunnels is difficult because so many variables differ. What they share is the fundamental challenge of moving Earth without bringing the surface down, of creating safe passage where none existed, of bending the city's infrastructure to human will without breaking it. Water tunnels bring fresh water into cities from distant sources. These tunnels are often enormous, large enough to walk through, and they carry millions of gallons per day. What makes water tunnels distinctive is that they must slope gently downwards so gravity moves the water, or they must be designed to handle pressure if water is pumped. They cannot have low points where sediment would accumulate or air would become trapped. The interior must be smooth to minimize friction and allow water to flow efficiently. Building a water tunnel requires thinking about hydraulics as much as geology, designing a path that accommodates both earth and fluid dynamics. Some water tunnels are ancient. Rome's aqueducts included underground sections that functioned as tunnels, built 2,000 years ago and still visible today. What makes these ancient tunnels so remarkable is that they were built without modern tools or knowledge. Yet, many still stand, testament to careful craftsmanship and an intuitive understanding of engineering principles. Modern engineers study these ancient works, sometimes with admiration, sometimes with puzzlement at methods that worked despite seeming improbable. The continuity across millennia is humbling, a reminder that the need to move water through Earth is timeless, connecting modern tunnel builders to ancestors who faced the same challenges with cruder tools but equal determination. Sewer tunnels carry waste away from cities, often following routes beneath rivers or through areas where surface sewers cannot reach. These tunnels must handle not just water but solid material, requiring designs that prevent clogging and allow periodic cleaning. The slope must be steep enough to keep material moving but not so steep that water rushes through while solids settle. What makes sewer tunnels so essential yet overlooked is their invisibility. They are taken for granted until they fail, at which point their importance becomes immediately and unpleasantly obvious. Building new sewer tunnels beneath established cities often means working in contaminated environments, requiring specialized equipment and procedures to protect workers from exposure to pathogens and toxic gases. The depth of sewer tunnels is carefully calculated. They must be deep enough to collect waste from buildings through gravity-fed connections, but not so deep that excavation becomes prohibitively expensive or maintenance becomes difficult. In some cities, sewer systems are layered, with different tunnels at different depths serving different neighborhoods or handling different flow volumes. This creates a three-dimensional maze beneath the streets, where one tunnel might pass over or under another, separated by only a few feet of earth. Coordinating these systems requires precise mapping and careful construction to ensure tunnels do not accidentally intersect or compromise each other's structural integrity. Utility tunnels carry pipes, cables, and conduits for electricity, telecommunications, gas, and other services. These tunnels allow maintenance without digging up streets repeatedly. A worker can enter the utility tunnel, walk to the problem location, and make repairs in a controlled environment. What makes utility tunnels so practical is access. Instead of excavating, locating the damaged section, repairing it, and refilling the excavation, work can be done quickly and cleanly underground. Cities that invested in utility tunnels decades ago continue benefiting from that foresight. Cities without them face constant street disruption as utilities are accessed and repaired through repeated excavation. Building utility tunnels requires coordination among multiple utility companies who may normally compete. Everyone must agree on layout, access rights, and maintenance responsibilities. What makes this cooperation so challenging is that utilities have different needs. Electrical cables generate heat and need ventilation. Gas lines require leak detection and isolation. Water pipes may leak occasionally and need drainage. Telecommunications cables need protection from electromagnetic interference. Fitting all these requirements into a single tunnel requires compromise and detailed planning. The result is a shared space that benefits everyone but belongs to no single entity, requiring ongoing governance and cooperation to manage effectively. Emergency egress is designed into every modern tunnel. People must be able to escape quickly if something goes wrong. In transit tunnels, this means cross passages connecting parallel tunnels every few hundred feet, allowing people to move from a tunnel with a problem to a safe tunnel nearby. Emergency exits lead to the surface, often through stairways in ventilation shafts. Lighting systems have battery backup so pathways remain visible even if main power fails. What makes egress design so important is that tunnels are inherently difficult to evacuate. There are only two directions to go, toward one portal or the other, and if both are blocked, people are trapped. Cross passages and emergency exits provide alternatives, giving people ways out even in worst-case scenarios. Fire is one of the most dangerous emergencies in a tunnel. Smoke fills the confined space quickly, and heat has nowhere to dissipate. Modern tunnels are designed with fire in mind. Materials used in construction are fire-resistant where possible. Ventilation systems can be reversed to push smoke away from evacuation routes. Fire suppression systems spray water or foam automatically when fire is detected. Despite all these measures, fires remain frightening events. Historical tunnel fires have caused casualties and led to major improvements in safety standards. What makes fire safety so challenging is that every tunnel is different, and solutions must be tailored to specific geometry, ventilation, and usage patterns. There is no universal template, only principles that must be adapted to each situation. Some tunnels serve multiple purposes. A tunnel might carry both a roadway and utilities, or both a transit line and pedestrian walkway. What makes multi-purpose tunnels so efficient is that they maximize use of expensive underground space. Excavating a tunnel costs so much that fitting multiple functions into one excavation makes economic sense. The challenge is design complexity. Different uses have different requirements that must all be met simultaneously. A road needs specific clearances and ventilation. Utilities need access and separation from each other. Pedestrians need lighting and safety barriers. Reconciling these needs requires careful spatial planning, often resulting in tunnels with multiple levels or separated sections, each optimized for its purpose but sharing the common excavation. Abandoned tunnels exist beneath many cities. Some were built for purposes that are now obsolete. Old utility tunnels that once carried coal or steam heating. Transit tunnels from lines that were rerouted or discontinued. Infrastructure from wars, such as bunkers or supply tunnels, now sealed and forgotten. What makes these abandoned spaces so intriguing is their mystery. They exist in the gaps of official records, sometimes known only through rumors or accidental discoveries. Occasionally they are rediscovered during new construction, surprising workers who break through into a void that should not be there. These forgotten tunnels are reminders that cities have hidden histories, layers of past decisions buried and built over. Some abandoned tunnels are repurposed. Old transit tunnels become storage areas or emergency shelters. Abandoned utility tunnels become routes for new cables or pipes. What makes repurposing attractive is that the excavation work is already done. Adapting an existing tunnel is usually cheaper than digging a new one. However, abandoned tunnels come with uncertainties. Their condition may be unknown. Records of what exists might be incomplete or lost. Accessing them might require breaking through sealed entrances or navigating collapsed sections. Repurposing becomes a careful process of exploration, assessment, and renovation, treating the old tunnel almost like an archaeological site that must be understood before it can be used again. Urban legends often grow around tunnels. Stories of ghost stations, hidden passages, secret government facilities, or lost workers who never emerged. What makes tunnels fertile ground for legends is their inaccessibility and mystery. Most people never see them beyond the finished portions opened to the public. The rest remains hidden, locked behind service doors or buried beneath newer construction. In this hidden space, imagination fills gaps in knowledge. Some legends have kernels of truth. There really are sealed stations and forgotten passages. Others are pure fiction, stories that reflect anxieties about what might exist beneath everyday streets. The legends become part of a city's folklore, giving the underground a mythic dimension. Tunnels also serve in emergencies. In some cities, Tunnel networks provide evacuation routes or shelter during disasters. Subway tunnels have been used as bomb shelters during wars. Service tunnels provide access for emergency responders to reach areas that might be cut off on the surface. What makes tunnels valuable in emergencies is their protection. Underground, people are shielded from weather, debris, and some threats that affect the surface. However, tunnels also present risks. Flooding can trap people. Ventilation failure can create dangerous air quality. Structural damage from earthquakes or explosions can cause collapses. Emergency planners must weigh these factors, determining when tunnels provide safety and when they become hazards. The environmental impact of tunnel construction is carefully managed in modern projects. Excavated material must be disposed of responsibly, often requiring testing for contamination before it can be moved. Water pumped from tunnels may contain sediment or pollutants that must be treated before discharge. Noise and vibration during construction must be controlled to minimize disturbance. What makes environmental management so complex is that impacts are not always obvious. Lowering groundwater tables can affect vegetation blocks away. Vibration can damage buildings in subtle ways that only appear months later. Responsible tunnel construction anticipates these impacts and implements mitigation measures, monitoring effects throughout the project and adjusting practices if problems emerge. Some cities have developed extensive tunnel networks over time. Paris has catacombs, sewers, and metro tunnels layered beneath the streets, creating a subterranean city that mirrors the surface. Tokyo's underground includes shopping arcades, transit lines, and utility tunnels woven together in a dense network. What makes these networks so impressive is not just their extent but their integration. Different systems connect and support each other, creating infrastructure that functions as a coherent whole rather than isolated pieces. This integration developed gradually as each new tunnel was planned to fit with existing ones, maintaining compatibility and creating opportunities for future connections. Planning for the future is essential when building tunnels. A tunnel built today might serve the city for a century or more. This long lifespan means that current decisions affect future generations who will inherit and use the infrastructure. What makes future planning so difficult is uncertainty. Planners cannot know how the city will grow, what technologies will emerge, or what challenges will arise decades from now. They can only build flexibility into designs where possible, leaving room for upgrades, connections, and adaptations. Tunnels that seem adequate for today's needs might be constrained tomorrow. Overbuilding provides margin for growth but increases cost. Finding the balance between present affordability and future capacity requires judgment and acceptance that perfect foresight is impossible. Some tunnels were built with future expansion in mind. Stations include shell spaces where additional platforms could be added later. Tunnels are sized to accommodate larger trains than currently run. Junction boxes and access points are installed for systems that do not yet exist but might be needed. What makes this foresight so valuable is that it reduces future construction difficulty. Adding capacity to an operating tunnel is extremely disruptive and expensive. Building that capacity in advance, even if unused for years, can save enormous cost and inconvenience later. The challenge is convincing funders to pay for capacity that is not immediately needed. It requires long-term thinking and trust that future needs will justify present investment. Tunnel boring machine technology continues to evolve. Machines are becoming larger, capable of excavating tunnels with diameters that once seemed impossible. They are becoming smarter, with sensors and automation allowing them to respond to ground conditions with minimal human intervention. They are becoming more versatile, able to handle a wider range of geology without requiring different equipment. What makes this evolution so exciting is that it expands what is possible. Tunnels that would have been impractical decades ago are now feasible. Projects that would have taken 10 years might now take 5. As technology improves, the economic calculations change, making tunneling more attractive relative to surface alternatives. Despite technological advances, tunneling remains fundamentally difficult. The Earth does not cooperate simply because tools improve. Unexpected conditions still arise. Water still seeps. Rock still fractures unpredictably. What technology provides is better tools to respond to these challenges, not elimination of the challenges themselves. The best tunnel boring machine still requires skilled operators who understand geology and can interpret what the machine is telling them. The most advanced monitoring still requires engineers who know what the data means and how to respond. Technology amplifies human capability but does not replace human judgment. Tunneling remains a craft where experience, intuition, and adaptability matter as much as equipment specifications. The noise of tunnel construction is distinctive. The whine of electric motors, the grinding of cutters against rock, the beeping of vehicles reversing, the hiss of hydraulics, the rumble of conveyor belts carrying muck away. What makes this soundscape so unique is its constancy. Unlike surface construction where noise comes and goes, tunnel construction is continuous. The machine operates around the clock. The sounds blend into a sustained industrial symphony that workers become accustomed to, learning to distinguish normal sounds from those that indicate problems. A change in pitch might mean cutters are dulling. A sudden quiet might mean equipment failure. Workers develop an ear for the tunnel's voice, listening to what it is saying through the sounds of machinery and earth. The smell underground is equally distinctive. Damp earth, diesel exhaust, rock dust, the metallic scent of drilling, occasionally the sulfurous smell of certain rock formations or the sewage smell if a tunnel intersects old drainage. What makes these smells so pervasive is that air circulation, while necessary, is imperfect. Smells linger in the confined space. Fresh air arriving from the surface brings temporary relief, but the underground odor always returns. Workers often do not notice after initial acclimatization, but visitors to tunnels under construction are always struck by the smell, a reminder that this is an environment far removed from normal experience. Temperature underground is relatively constant. The earth insulates, maintaining a temperature close to the annual average for that location regardless of surface weather. In winter, tunnels feel warm compared to outside. In summer, they feel cool. What makes this stability comforting is predictability. Workers do not deal with extreme heat or cold. However, machinery generates significant heat, and in deep tunnels, geothermal gradients can make the environment quite warm. Cooling systems may be necessary to keep conditions tolerable. The combination of heat, humidity, and poor air circulation can make deep tunnels uncomfortable despite the Earth's moderating effect. Lighting in tunnels is crucial but challenging. Natural light does not penetrate beyond the portal. Everything must be artificially illuminated. Work lights are positioned to illuminate the cutting face and immediate work area brightly, but beyond that glow, the tunnel stretches into darkness. What makes this lighting environment so disorienting initially is the lack of reference points. There are no windows, no sky, no variation in light quality that indicates time passing. Day and night become irrelevant. Workers lose track of whether it is morning or evening outside. Time is measured by shifts and progress, not by the sun's position. The tunnel becomes a timeless space where work continues regardless of what is happening on the surface. Psychological aspects of tunnel work should not be underestimated. Working underground in confined spaces with limited escape routes requires mental resilience. Some people find it unbearable and cannot continue despite physical capability. Others find it oddly peaceful, preferring the enclosed, focused environment to the chaos of surface construction. What makes the psychology so individual is that people respond differently to confinement. For some, the tunnel feels protective, a space separated from surface concerns. For others, it feels oppressive, a constant weight pressing down. Tunnel projects carefully screen workers, ensuring that those who work underground are comfortable in that environment, because psychological distress can compromise safety and productivity. Camaraderie helps. Working in challenging conditions bonds crews together. Shared hardship creates solidarity. Workers develop trust in each other because their safety depends on collective attention and care. What makes this bonding so strong is that tunnel work cannot be done alone. It requires teams coordinating efforts, communicating constantly, and supporting each other through long shifts in difficult conditions. When the project ends, workers often remain in contact, connected by the shared experience of having built something substantial together under the earth. The tunnel becomes not just a physical structure but a social one, a network of relationships formed in darkness and maintained afterward in light. Tunnel work schedules are demanding. Because machines run continuously, shifts operate around the clock. Workers might find themselves on night shifts for weeks, sleeping during the day and working when the surface world sleeps. This disrupts normal life rhythms. What makes these schedules tolerable is typically high pay and the knowledge that the project is temporary. Workers endure difficult schedules for months or years, knowing that eventually the tunnel will finish, and they will move to a different project or return to more conventional work. The pay and the pride in accomplishment compensate for the disruption, but tunnel work is rarely something people can sustain indefinitely. It is intense, focused, and exhausting in ways that eventually require respite. Historical tunnels were built with far more manual labor than modern ones. Workers with hand tools excavated rock, carried debris in baskets, and supported walls with timber. Progress was measured in feet per week rather than feet per day. What makes those achievements so remarkable is the sheer effort involved. Tunnels like the Thames Tunnel in London, completed in 1843, took nearly 20 years and cost many lives. Workers faced constant flooding, cave-ins, and disease. Yet they persisted, driven by need and the promise of employment. Modern tunnel workers, while facing real challenges, have incomparably better conditions thanks to technology, regulation, and cultural changes that value workers' safety and dignity. Some historical tunnels were engineering marvels that pushed contemporary capabilities to their limits. The Hoosick Tunnel in Massachusetts, completed in 1875, took 24 years and pioneered the use of nitroglycerin for blasting. The Mont Cenis Tunnel through the Alps, completed in 1871, was the first major tunnel to use pneumatic drills powered by compressed air. These projects were learning experiences where techniques were developed through trial and error, often at great cost. What makes studying them so valuable is understanding how knowledge accumulated. Each project taught lessons that informed the next. Failures revealed dangers. Successes validated methods. Over time, tunneling evolved from a dangerous gamble to a predictable, though still challenging, engineering discipline. Geology textbooks are written partly from tunnel experience. When tunnels are excavated, they expose rock formations that can be studied directly. Geologists descend into tunnels to observe layers, faults, and structures that are otherwise hidden beneath the surface. What makes tunnels so valuable scientifically is that they provide three-dimensional exposures showing not just surface features but also how geology changes with depth. Observations made during tunnel construction have refined understanding of local geology, sometimes revealing surprises that require rewriting geological maps. In this way, infrastructure projects contribute to pure science, expanding knowledge even as they serve practical purposes. Some minerals or fossils are discovered during tunneling. A tunnel might break into a cavity lined with crystals or cut through a layer containing preserved ancient life. These discoveries can be scientifically significant but also create dilemmas. Should work stop to allow scientific study? How long is reasonable? Who owns the specimens? What makes these situations so delicate is that competing interests must be balanced. The scientific value of a rare find must be weighed against the cost of construction delays and the project's importance to the city. Usually compromises are found, with documentation and sample collection happening quickly so work can resume, but tensions remain between scientific curiosity and practical necessity. Groundwater mapping improves significantly from tunnel projects. As tunnels are excavated, water inflows reveal where aquifers exist and how water moves underground. This information benefits future projects and helps manage water resources more broadly. What makes this knowledge so useful is that it is direct rather than inferred. Surface studies can predict where water might be, but tunnel construction confirms it. Flow rates can be measured. Water chemistry can be analyzed. Seasonal variations can be observed over the course of construction. This data becomes part of the city's geological database, informing decisions about water supply, contamination risks, and future construction. Archaeologists sometimes accompany tunnel projects in historically significant areas. In cities with ancient pasts, any excavation might uncover artifacts or structures. Archaeologists monitor work, ready to step in if something significant appears. What makes this collaboration so interesting is the blending of timelines. Modern engineers carving tunnels for future use may pass through layers created by ancient engineers building foundations or infrastructure for their own era. When these layers intersect, there is a moment of connection across centuries, a tangible reminder that the impulse to build, to connect, to solve problems through construction is not new but has driven human societies for millennia. Tunnel projects often include public outreach. Visitor centers are established where people can learn about the project, see displays of equipment, and sometimes observe work through windows or video feeds. What makes this outreach so important is building public support. When people understand what is being built and why, they are more patient with disruptions and more willing to support funding. Seeing the scale of the machines, the complexity of the work, and the professionalism of the crews builds appreciation. What was abstract, just a line on a map and a budget figure, becomes real, a tangible project undertaken by real people doing impressive work. Schools bring students to tunnel projects. Young people see engineering in action, often inspiring interest in careers they had not considered. What makes these visits so impactful is immediacy. A tunnel boring machine is vastly more impressive in person than in pictures. The scale, the noise, the sense of purposeful activity all make lasting impressions. Some students who visit tunnel projects as children return years later as engineers, inspired by what they saw. Tunnel construction becomes not just infrastructure but also education, showing the next generation what is possible through technical skill and determination. Media coverage of tunnel projects ranges from celebratory to critical. Groundbreaking ceremonies are covered as civic achievements. Breakthroughs are celebrated with headlines and photos. But delays, cost overruns, and problems also draw attention, sometimes leading to harsh criticism. What makes media relations so challenging for tunnel projects is that problems are inevitable and delays are common given the complexity and unpredictability of underground work. Managing expectations and communicating honestly about challenges while maintaining public confidence requires skill. Successful projects balance transparency about difficulties with steady progress reports that demonstrate value being created. Political support is essential for major tunnel projects. Funding requires government approval. Permits must be obtained from multiple agencies. Neighborhood concerns must be addressed. What makes navigating this political landscape so demanding is that different stakeholders have different priorities. Business groups want projects completed quickly. Environmental groups want impacts minimized. Residents want disruption reduced. Politicians want visible progress without controversy. Balancing these interests requires patience, negotiation, and often compromise. Tunnel projects become political as much as technical undertakings, requiring leadership that can build coalitions and maintain support through the long construction period. Some tunnel projects become controversial despite their benefits. Opposition can arise from concerns about cost, disruption, environmental impact, or disagreement over whether the tunnel is the right solution. What makes these controversies so challenging is that they can delay or even cancel projects after significant planning has occurred. Years of work and millions in expenditures can be lost if political support evaporates. Projects must therefore engage communities early, addressing concerns before opposition solidifies. Listening to criticism and adjusting plans where reasonable can prevent conflicts. However, some opposition may be intractable, requiring decision-makers to weigh whether proceeding despite controversy is justified by the project's importance. Finishing a tunnel is gradual. There is no single moment when suddenly the tunnel is complete. Systems are commissioned incrementally. Testing occurs in phases. Initial operations may be limited, expanding as confidence grows. What makes this gradual completion so different from surface construction is invisibility. A building's completion is obvious. A tunnel's completion happens mostly underground, visible only to those involved. The public experiences completion only when the tunnel opens for use, but that opening represents the culmination of work that has been finishing incrementally for months. The transition from construction to operation is a slow handoff from builders to operators, with overlap as systems are tested and adjusted. Opening day is ceremonial. Officials give speeches. First rides or drives through the tunnel are celebrated. Media covers the event. What makes opening day so significant emotionally is that it represents transformation. The project shifts from disruption to benefit. The tunnel stops being a construction site and becomes infrastructure. For workers who built it, opening day is bittersweet. Their work is validated, but their role is finished. For the public, it is a beginning, the start of using something that has been anticipated for years. The tunnel enters service and, within weeks or months, it becomes normal, another part of the city's fabric that people rely on without thinking about how it came to be. Long-term maintenance begins immediately. Tunnels require constant care to remain safe and functional. Water infiltration must be managed. Structural elements must be inspected for deterioration. Systems must be serviced and eventually replaced. What makes tunnel maintenance so important is that problems underground are difficult and expensive to fix once they become severe. Catching issues early, through regular inspection and preventive maintenance, avoids costly failures later. Maintenance crews develop deep familiarity with their tunnels, learning individual characteristics and quirks. They become stewards, preserving the infrastructure for future generations. Some tunnels last centuries with proper care. Roman aqueducts still function. 19th century rail tunnels still carry trains. What makes this longevity possible is solid initial construction and ongoing maintenance. A well-built tunnel in stable geology can endure almost indefinitely if water is managed and the structure is maintained. This longevity represents extraordinary value. The initial cost, while high, is amortized over many decades or even centuries. Each year of service reduces the effective cost per user to smaller and smaller amounts until the infrastructure essentially becomes free, having paid for itself many times over. This long-term value is what justifies initial investment, though it requires vision to appreciate value that will accrue over generations. Eventually, some tunnels are retired. Changes in technology or city layout may render a tunnel obsolete. When this happens, the tunnel may be sealed and abandoned or repurposed for new uses. What makes these endings so poignant is that tunnels outlast the need they were built to serve. A tunnel built with great effort for a specific purpose becomes irrelevant as the world changes. Yet even abandoned, the tunnel remains, a buried monument to past needs and past solutions. Future generations may rediscover it and wonder at its purpose, or it may remain hidden indefinitely, a forgotten cavity in the earth. The impact of tunnels on cities is profound but often unappreciated. Tunnels enable density by moving people efficiently without consuming surface space. They protect infrastructure from weather and interference. They allow cities to grow beyond surface limitations. What makes this impact so easy to overlook is that tunnels work by disappearing. The best infrastructure is invisible, noticed only in its absence. When a tunnel functions correctly, users think only about their destination, not the passage that makes reaching it possible. This invisibility is success. The tunnel serves quietly, asking nothing, providing connection, enabling the city's life to flow smoothly. Tunnels also shape property values and neighborhood development. Areas near tunnel entrances become more accessible and often more valuable. What was once remote becomes connected. This transformation can benefit neighborhoods, bringing investment and opportunity. It can also bring displacement as rising costs push out long-time residents. What makes this impact so complex is that it is indirect and unfolds over years. The tunnel itself is neutral, simply providing transportation. But its presence changes the economic geography of the city in ways that planners attempt to anticipate but cannot fully control. Tunnels become catalysts for change that extends far beyond their physical footprint. In some cities, the underground is becoming as important as the surface. Tokyo, Hong Kong, and Montreal have developed extensive underground cities with shopping, dining, and connections between buildings, all linked by transit tunnels. What makes these developments so fascinating is that they create parallel urban environments. People can spend entire days underground, moving between work, shops, and transit without surfacing. This underground urbanism is possible only because of tunnels that provide access, ventilation, and connection. The tunnel stops being merely infrastructure and becomes space, environment, a place where urban life happens rather than just passes through. Future tunneling may go deeper than ever before. As surface and shallow underground become more crowded, projects may push into deeper geology to find available space. What makes deep tunneling so challenging is that pressure, temperature, and water volume all increase with depth. Equipment must withstand harsher conditions. Rock behaves differently under extreme pressure. Yet the technology to tunnel deeper is developing, promising access to three-dimensional space that cities have not yet utilized. This vertical expansion underground mirrors historical expansion upward into taller buildings, both responses to the same constraint of limited horizontal space. Automated tunneling is developing as well. Remote-controlled and eventually autonomous tunnel boring machines may reduce the need for workers at the tunnel face, improving safety by removing people from the most dangerous locations. What makes automation promising is consistency. Machines do not tire or lose focus. They can optimize cutting parameters continuously based on sensor feedback. However, automation also raises concerns about employment and the loss of expertise that comes from hands-on experience. As with automation in many fields, the transition will likely be gradual, with humans and machines working together before machines become fully independent. The materials science of tunneling continues advancing. New concrete formulations cure faster and stronger. Composite materials offer lighter weight and better corrosion resistance. Sealants and waterproofing materials become more effective and durable. What makes materials science so crucial is that the tunnel's longevity depends on the materials used to build it. Choosing the right materials for specific conditions requires understanding chemistry, engineering, and geology together. As materials improve, tunnels can last longer, require less maintenance, and perform better under challenging conditions. Each material advance expands what is possible underground. Sensing technology transforms how tunnels are monitored. Fiber optic cables embedded in tunnel linings can detect strain, temperature changes, and movement, providing continuous data about structural health. Acoustic sensors listen for sounds that indicate developing problems. Cameras with image recognition identify cracks or deterioration automatically. Makes this monitoring so valuable is that it shifts maintenance from reactive to predictive. Instead of waiting for problems to become obvious, small changes can be detected early when repairs are simpler and cheaper. The tunnel becomes self-aware in a sense, continuously reporting its own condition and asking for attention when needed. Climate change is creating new challenges for tunnel infrastructure. More intense rainfall can overwhelm drainage systems. Rising sea levels threaten coastal tunnels with flooding. Changing groundwater patterns alter the pressures tunnels must withstand. What makes adapting to these changes so important is that tunnels, once built, are difficult to modify. They must be designed with future conditions in mind, accounting for changes that may occur over their long service lives. This requires climate modeling, risk assessment, and often building in extra capacity or protective measures that may not seem necessary today but will become essential as conditions change. Resilience is becoming a design priority. Tunnels are being planned to withstand not just normal conditions but also extreme events like earthquakes, floods, or other disasters. Redundancy is built in so that if one system fails, backups maintain safety. What makes resilience so critical is that tunnels serve essential functions. When a tunnel fails, entire parts of cities can become disconnected. Ensuring that tunnels can survive rare but devastating events requires investing in protective measures that may never be used but provide insurance against catastrophe. The cost is justified by the immense disruption that failure would cause. Tunnel projects are increasingly international collaborations. Expertise developed in one country is applied in another. Equipment manufacturers, engineering firms, and construction companies work across borders. What makes this internationalization so beneficial is that it spreads knowledge and best practices. A technique developed for Tokyo's subway can inform projects in London or New York. Lessons learned from failures in one place prevent repeating mistakes elsewhere. Tunneling becomes a global discipline with shared standards and continuous improvement driven by experiences worldwide. Training the next generation of tunnel engineers and workers is essential. As experienced professionals retire, their knowledge must be transferred. What makes this transfer so challenging is that much tunneling expertise is tacit, learned through experience rather than taught explicitly. Mentorship programs pair novices with veterans who share insights gained from years underground. Simulators allow practice without risk. Apprenticeships provide hands-on learning in real conditions. Despite these efforts, some knowledge is inevitably lost as generations change, making documentation and knowledge preservation increasingly important. Universities are establishing research programs focused on underground construction. What makes academic involvement so valuable is that it brings scientific rigor to problems that might otherwise be solved only through trial and error. Research can optimize cutting tool design, improve ground modeling, develop better materials, and advance understanding of how Earth behaves under various conditions. This research feeds back into practice, improving tunnel construction incrementally. The relationship between academia and industry benefits both, with practical problems inspiring research and research findings improving practice. Public perception of tunnels is gradually shifting. Once seen as dark, dangerous places, tunnels are increasingly recognized as sophisticated infrastructure enabling modern urban life. What makes this shift so encouraging is that it builds support for investing in underground infrastructure. As people understand the complexity and value of tunnels, they become more willing to fund new projects and maintain existing ones. This cultural change is subtle but important, affecting political will and public patience with the disruptions that construction inevitably brings. Some cities are planning underground parks and recreational spaces. Abandoned tunnels or purpose-built caverns can be transformed into green spaces, art galleries, or cultural venues. What makes these projects so creative is that they reimagine underground space as something more than purely functional. The underground can be pleasant, even beautiful, if designed thoughtfully. Natural light can be brought down through shafts. Plantings can thrive with artificial lighting. These projects challenge assumptions about what underground space can be, suggesting possibilities beyond transportation and utilities. The psychology of underground space is being studied more carefully. How do people experience enclosed environments? What design choices make underground spaces feel comfortable rather than oppressive? What lighting, colors, materials, and spatial arrangements work best? What makes this research so practical is that it directly improves design. Tunnels and underground stations designed with psychological comfort in mind see higher use and greater public acceptance. Understanding human response to underground environments makes infrastructure more humane, serving not just functional needs but also emotional ones. Art in tunnels is becoming more common. Murals, sculptures, and installations transform utilitarian spaces into experiences. What makes art so valuable in tunnels is that it gives people something interesting to observe during their passage. A commute becomes more pleasant. A walk through a utility corridor becomes memorable. Art also signals care, suggesting that the space matters and deserves aesthetic attention. This elevates tunnels from mere infrastructure to civic spaces worthy of beauty. Lighting design in tunnels has evolved dramatically. Early tunnels were poorly lit, often just dim bulbs providing minimal visibility. Modern tunnels feature thoughtful lighting that illuminates effectively while consuming less energy and creating pleasant environments. LED technology allows varied color temperatures and intensities. Dynamic lighting can change throughout the day or respond to conditions. What makes lighting so transformative is that it fundamentally shapes how people experience underground space. Good lighting makes spaces feel safe, comfortable, and welcoming. Poor lighting creates anxiety and discomfort. The difference is dramatic despite seeming subtle. Sound design is also being considered. Hard tunnel surfaces reflect noise, creating echoes and making spaces acoustically harsh. Sound-absorbing materials can reduce noise levels. Careful design of curves and surfaces can prevent sound from amplifying unpleasantly. What makes acoustic design so important is that constant loud noise fatigues people and creates stress. Quieter tunnels are more pleasant to use and work in. As with lighting, acoustic quality dramatically affects experience despite often going unnoticed consciously. People simply feel better in well-designed acoustic environments without necessarily understanding why. The social aspects of tunnel use are interesting. Transit tunnels become temporary communities where strangers share space briefly. Social norms develop around behavior in these shared underground spaces. What makes these social dimensions so subtle is that they emerge without planning. People learn to stand right and walk left on escalators. They learn where to wait and how to board. These unwritten rules facilitate smooth flow and minimize conflict. They represent collective adaptation to shared infrastructure, tiny examples of spontaneous social organization. As we near the end of this exploration, it is worth reflecting on what tunnels represent. They are, in one sense, simply voids carved through earth. But they are also profound achievements of human cooperation, persistence, and ingenuity. Tunnels are built by many people working toward a common goal, coordinating efforts across years, solving problems as they arise, and creating something that will outlast them. What makes tunnels so quietly remarkable is this combination of ambition and humility. The scale is grand, yet the work proceeds methodically, patiently, 1 foot at a time. Tunnels do not shout their existence. They serve quietly, asking nothing but maintenance, providing connection without demanding attention. The darkness of a tunnel is absolute when lights are off. It is a darkness you can feel, heavy and complete. Yet when illuminated, a tunnel becomes a passage full of purpose and activity. This transformation from darkness to usefulness feels symbolic. Through effort and ingenuity, humans take empty space and make it meaningful. The tunnel goes from absence to presence, from nothing to something essential. That transformation, repeated in cities around the world, represents the constructive impulse that builds civilization itself. The will to connect, to make access easier, to solve problems through making, through building, through persistence. Tunnels also teach patience. They cannot be rushed. The earth yields only at its own pace. Forcing leads to accidents and failures. Success comes from steady work, consistent attention, and respect for the medium being worked. What makes this lesson so valuable is its broader applicability. Many important things cannot be rushed. They require sustained effort over time, accepting that progress may be slow but trusting that accumulation of small advances eventually completes great works. Tunnels are physical manifestations of this truth, reminders that patience and persistence create lasting achievements. The people who build tunnels deserve recognition that they rarely receive. They work in difficult conditions, underground, often for years, creating infrastructure that most users never think about. What makes their work so admirable is dedication to craft and purpose. They know that most people will never see what they build or understand the challenges overcome. Yet they proceed anyway, taking pride in work well done regardless of recognition. This quiet professionalism sustains infrastructure projects and deserves appreciation. Behind every tunnel is a story of human effort, of problems solved, of skill applied with care, of individuals contributing to something larger than themselves. The future of cities depends increasingly on what exists underground. As populations concentrate in urban areas, the surface becomes more crowded and contested. Every street, every park, every open space serves multiple purposes and faces competing demands. The underground offers dimension that can relieve this pressure without consuming visible space. What makes underground development so essential for future cities is that it provides room to grow without sacrificing what makes cities livable on the surface. Parks can remain green. Streets can carry pedestrians and cyclists. Buildings can be spaced reasonably. All of this becomes possible when the necessary but unglamorous infrastructure of utilities, transit, and storage moves below ground. This shift requires changing how we think about urban space. Traditionally, cities were planned in 2 dimensions, with height added later as buildings grew taller. Now cities must be planned in 3 dimensions, considering not just what sits on the surface but also what exists below and how underground and surface layers interact and support each other. What makes this three-dimensional thinking so challenging is that it requires coordination across systems that have traditionally operated independently. Transit planners, utility companies, building developers, and city managers must all consider the underground together rather than separately. This integration is developing slowly but represents a fundamental evolution in urban planning. Some cities are creating comprehensive underground master plans, mapping what exists and designating zones for future development. What makes these plans so valuable is that they bring order to what could otherwise become chaotic. Without planning, different agencies might excavate in conflicting ways, creating problems that are expensive to resolve later. With planning, underground development can proceed efficiently, with different uses coexisting and future expansion anticipated. The underground becomes managed space rather than a frontier claimed piecemeal by whoever gets there first. Legal frameworks for underground space are also evolving. Property rights traditionally focused on surface land. As underground development intensifies, questions arise about who owns rights to space beneath the surface, how deep those rights extend, and how conflicts between different underground uses should be resolved. What makes these legal questions so complex is that underground space does not map neatly onto surface property boundaries. A tunnel might pass beneath hundreds of surface properties. Whose permission is needed? How should they be compensated if their underground space is used? These questions lack clear answers in many jurisdictions and are being resolved gradually through legislation and case law. Economics of underground development are distinctive. The high upfront cost of tunneling means that projects often appear expensive compared to surface alternatives. However, when lifecycle costs are considered, including maintenance, land acquisition, and the value of preserving surface space, underground options become more competitive. What makes this economic analysis so important is that it shapes whether cities invest underground or attempt to continue growing on the surface. As surface space becomes scarcer and more valuable, the economic case for underground development strengthens. Cities that invest early in underground infrastructure position themselves better for future growth than cities that delay and must eventually undertake more disruptive and expensive projects when options are limited. Financing tunnel projects requires creative approaches. Traditional funding through taxes or bonds remains common, but other methods are emerging. Public-private partnerships allow private investment in exchange for revenue from operations. Value capture mechanisms tax the increased property values that result from new infrastructure, using that revenue to pay for the infrastructure itself. What makes these financing mechanisms so important is that they enable projects that might not proceed if dependent solely on government funding. They also align incentives, linking those who benefit from infrastructure to those who pay for it. International development banks and agencies increasingly support tunnel projects in developing cities. What makes this support so crucial is that many growing cities need underground infrastructure but lack capital for the massive upfront investments required. International support can accelerate projects that would otherwise take decades to fund domestically. These investments pay dividends in urban efficiency and quality of life, helping cities accommodate growth without sprawling endlessly or becoming paralyzed by congestion. Tunnels become tools of sustainable development, enabling density while maintaining livability. Climate adaptation is becoming a central concern in tunnel planning. In coastal cities, rising seas threaten to flood tunnels that were designed with older sea level assumptions. Retrofit projects are underway to add flood barriers, improve pumping capacity, and seal vulnerable sections. What makes climate adaptation so challenging for tunnels is that they were built for long service lives with specific assumptions about conditions. Changing those conditions midlife requires expensive modifications to infrastructure that was never designed to be easily altered. This highlights the importance of building climate resilience from the start, designing for conditions that may not exist today but will emerge over the tunnel's lifetime. Some tunnels are being designed with adaptive capacity, features that allow modification as conditions change. Extra space in cross-sections allows for adding systems later. Flexible connections permit rerouting. Modular components can be replaced as technology advances. What makes adaptive design so forward-thinking is that it acknowledges uncertainty. Designers cannot predict exactly what future needs will be, but they can create flexibility that allows response to those needs when they become clear. This approach costs more initially but provides value over time by reducing the cost and disruption of future modifications. The intersection of tunneling with new technologies is creating interesting possibilities. Autonomous vehicles might use dedicated underground highways, separating them from pedestrians and cyclists on the surface. Hyperloop systems propose very high-speed transit in near-vacuum tunnels. Underground freight systems could move goods beneath cities, reducing truck traffic on streets. What makes these proposals so intriguing is that they reimagine what tunnels can carry and how transportation can be organized. Not all will succeed, but experimentation is valuable. Some ideas that seem far-fetched today may become standard infrastructure decades from now, just as subways seemed improbable before they transformed urban mobility. Energy storage is another potential underground use. Large batteries or pumped hydro storage could be located in caverns beneath cities, providing grid stability without consuming surface space. What makes underground energy storage so practical is that it separates the storage function from surface activities while keeping it close to where energy is needed. Temperature stability underground also benefits some battery technologies. As renewable energy becomes more prevalent, storage becomes essential, and underground locations offer possibilities that surface sites cannot match. Data centers are increasingly moving underground. The stable temperatures, physical security, and protection from weather that tunnels and caverns provide make them attractive for housing servers. What makes this trend so interesting is that it represents another use for underground space beyond traditional infrastructure. Digital infrastructure is joining physical infrastructure below ground, both serving the same urban populations but in different ways. The underground becomes not just a place for movement and utilities but also for the information processing that increasingly defines modern cities. Agriculture might eventually move underground in some cities. Vertical farms in tunnels or caverns could produce food locally using artificial lighting. What makes underground agriculture so appealing in theory is that it uses space that cannot support conventional development while bringing food production closer to consumers. Challenges remain around energy costs for lighting and the economics of production, but as technology improves and surface space becomes more precious, underground farming may become viable. This would represent a remarkable shift, turning spaces excavated for one purpose into productive environments for another. Cultural attitudes toward underground space vary globally. Some cultures have traditions of living partially underground, using caves or excavated homes. Others view underground space with suspicion or discomfort. What makes these cultural differences so important for infrastructure development is that they affect public acceptance of underground solutions. In cultures comfortable with underground environments, ambitious projects face less resistance. In cultures where underground space is viewed negatively, even necessary projects may struggle for support. Understanding and respecting these attitudes while gently expanding what people consider acceptable becomes part of successful project development. Education about underground infrastructure can shift attitudes. When people understand what exists beneath their feet and how it serves them, appreciation grows. What makes education so transformative is that it replaces vague unease with concrete knowledge. The underground stops being an unknown void and becomes recognized as carefully engineered space serving essential functions. Museums of urban infrastructure, tunnel tours, and educational programs all contribute to this understanding. As knowledge spreads, support for maintaining and expanding underground infrastructure increases. The environmental benefits of tunneling are sometimes overlooked. By moving infrastructure underground, surface land can be preserved for parks, wildlife habitat, and agriculture. What makes this conservation so valuable is that surface ecosystems are far more diverse and productive than underground voids. Every subway tunnel represents streets that do not need widening, parking lots that do not need building, and surface space that can remain in more beneficial uses. The environmental cost of tunneling must be weighed against the environmental benefit of surface preservation. In many cases, the balance favors underground development despite the energy and resources required for construction. Noise pollution is dramatically reduced when infrastructure moves underground. Traffic noise, train noise, and industrial sounds that would be disruptive on the surface become contained and manageable underground. What makes this benefit so important for quality of life is that chronic noise exposure affects health and well-being. Quieter cities are more pleasant and healthier. By accepting the cost and complexity of building underground, cities can create surface environments that are more peaceful and conducive to human flourishing. The tunnel takes on the burden of noise, so the surface does not have to. Air quality also improves when pollution sources move underground. Vehicle exhaust in road tunnels can be captured and filtered before release rather than dispersing at ground level where people breathe it. What makes this pollution control so effective is concentration. Emissions collected in tunnels are easier to treat than diffuse pollution spread across many streets. This creates opportunities for cities to improve air quality while accommodating the vehicles that currently seem necessary. As electric vehicles become more common, underground air quality will improve further, making underground roads and tunnels cleaner and more pleasant. The role of tunnels in emergency response is significant. Underground transit can continue operating during surface weather events. Utility tunnels allow repairs without exposing workers to storms or extreme temperatures. What makes this reliability so crucial is that cities depend on infrastructure functioning consistently. When surface conditions make work dangerous or impossible, underground access provides alternatives. This resilience benefits not just daily operations but also emergency response when rapid repairs or access can prevent minor problems from becoming catastrophes. Conversely, tunnels themselves can be vulnerable during certain emergencies. Earthquakes can cause collapses or damage that is difficult to repair. Flooding can fill tunnels rapidly, potentially trapping people. Fires create smoke with nowhere to disperse. What makes tunnel safety so important is that these low-probability events can have severe consequences. Design must account for these rare scenarios through emergency exits, ventilation systems that can evacuate smoke, structural reinforcement in seismic zones, and flood barriers where appropriate. The goal is not eliminating risk entirely, which is impossible, but reducing it to acceptable levels through thoughtful engineering and planning. Training for tunnel emergencies is specialized. Responders must be comfortable working underground, familiar with tunnel layouts, and equipped with appropriate gear. What makes this training so essential is that tunnel emergencies differ fundamentally from surface ones. Navigation is more constrained. Smoke behaves differently. Communication can be difficult. Regular drills and exercises prepare responders for scenarios they hope never to face. This preparation means that if emergencies occur, response can be swift and effective, minimizing harm. Public confidence in tunnel safety comes from demonstrated reliability. When tunnels operate for decades without major incidents, people come to trust them. What makes maintaining this confidence so important is that it sustains use. If people fear tunnels, they avoid them, rendering infrastructure investments ineffective. Safety records must be communicated clearly. When incidents occur, responses must be transparent and improvements visible. Trust, once lost, is difficult to rebuild. Maintaining it requires consistent attention to safety and honest communication about both successes and failures. The aesthetics of tunnel portals and ventilation structures matter more than might be expected. These surface elements represent the tunnel to people who never go inside. What makes their design so important is that they shape public perception. A beautiful, well-integrated portal suggests a quality project. A crude, ugly structure suggests carelessness. Cities increasingly treat these elements as architecture worthy of design attention rather than purely functional necessities. This attention to appearance reflects respect for communities that host infrastructure and recognition that beauty has value even in utilitarian structures. Community input during tunnel planning has become standard practice. Public meetings, comment periods, and stakeholder consultations allow affected communities to voice concerns and influence decisions. What makes this participation so valuable is that it identifies issues planners might overlook and builds local support. When communities feel heard, even if not all their preferences are accommodated, they are more likely to support projects. Meaningful engagement takes time and resources but prevents conflicts that could delay projects far longer than engagement itself requires. Equity considerations are increasingly central to tunnel planning. Who benefits from new infrastructure? Who bears the burden of construction disruption? Are disadvantaged communities being served or bypassed? What makes these equity questions so important is that infrastructure decisions shape opportunity. Access to transportation affects employment, education, and quality of life. Tunnel projects should serve all communities fairly, not just those with political influence or wealth. This requires conscious attention to routing, station placement, and ensuring that the benefits of improved mobility are broadly shared. Historic preservation can conflict with tunnel projects. Excavation beneath historic districts risks damaging old buildings. Tunnel portals may disrupt historic streetscapes. What makes these conflicts so difficult is that both preservation and infrastructure serve important values. Preserving the past maintains cultural continuity and identity. Building infrastructure serves present and future needs. Finding balance requires creativity, sometimes routing tunnels to avoid sensitive areas, sometimes using special construction methods that minimize disturbance, sometimes accepting that some impact is unavoidable but can be mitigated through careful design. The bureaucracy of tunnel projects is immense. Permits from numerous agencies, compliance with countless regulations, coordination across multiple jurisdictions, all create administrative complexity that can rival technical challenges. What makes navigating this bureaucracy so demanding is that it requires different skills than engineering. Patience, diplomacy, attention to procedural detail, and persistence become as important as technical expertise. Projects can be delayed more by administrative hurdles than by construction difficulties. Streamlining approval processes without compromising safety or environmental protection is an ongoing challenge for cities seeking to build infrastructure more efficiently. International standards for tunnel safety and construction are developing gradually. Organizations bring together experts from multiple countries to share best practices and develop recommendations. What makes international standardization so beneficial is that it raises the floor for quality everywhere. Techniques proven effective in one country become available to others. Mistakes made in one project inform others so the same errors are not repeated. However, standardization must also respect local conditions. What works in one geological or cultural context may not transfer directly to another. Standards must balance universal principles with local adaptation. The role of innovation in tunneling is continuous. New cutting tools, better materials, improved surveying techniques, and refined methods emerge from each generation of projects. What makes this innovation so important is that tunneling, despite ancient roots, remains a developing field. There is no perfect solution, only better solutions than existed before. Each improvement makes future projects safer, faster, or more economical. Innovation happens not through revolution but through patient refinement, taking what works and making it slightly better, accumulating improvements until what once seemed impossible becomes routine. Universities and research institutes play crucial roles in advancing tunneling technology. They conduct experiments too expensive or risky for commercial projects. They develop theoretical understanding that informs practical applications. They train the engineers and scientists who will lead future projects. What makes academic contribution so valuable is that it thinks beyond immediate needs to long-term possibilities. Research today may not pay off for decades but will eventually enable projects that current technology cannot handle. Investing in research is investing in future capability. The documentation of tunnel projects creates valuable knowledge resources. Detailed records of geology encountered, problems faced, solutions implemented, and outcomes achieved become guides for future projects. What makes documentation so essential is that tunneling knowledge is scattered. Each project encounters unique conditions, and lessons learned in one place may be highly relevant to a project elsewhere. Systematic documentation and sharing of experience accelerate learning across the entire field. What one project discovers benefits everyone who comes after, creating a cumulative knowledge base that makes each successive generation of tunnels better than the last. Some of the most valuable documentation comes from problems and failures. When things go wrong, understanding why prevents repetition. What makes failure so instructive, though painful, is that it reveals limits clearly. Success can result from many factors, some not fully understood. Failure demands explanation. Investigating failures thoroughly and sharing findings openly, though sometimes uncomfortable, serves the greater good by making future work safer and more reliable. A culture that learns from mistakes rather than hiding them is healthier and more capable of improvement. As night deepens and our journey through these underground passages comes to a close, consider what you have learned tonight. Tunnels are more than engineering achievements. They are acts of faith in the future, investments made by one generation for the benefit of those to come. They represent patience, persistence, and cooperation on a scale that individuals rarely experience directly but collectively make possible. Beneath the cities where millions live and work, these passages carry people, water, waste, power, and information, quietly enabling the complexity of modern urban life. What makes tunnels so worthy of wonder is this quiet service. They ask for nothing. They simply exist, performing their functions day after day, year after year, decade after decade. The best tunnels are those you never think about consciously, yet would desperately miss if they disappeared. This invisible reliability is the highest achievement of infrastructure, so successful that it becomes taken for granted, which is exactly as it should be. As you settle deeper into rest, you can let these thoughts drift away. The tunnels will continue their work without your attention. Somewhere beneath a city, perhaps beneath your own, passages stretch through darkness, carrying trains through ancient bedrock, guiding water from distant sources, holding cables that connect distant places. This work continues regardless of whether anyone watches or thinks about it. The tunnels do not need recognition or praise. They need only maintenance and occasional appreciation for what they quietly make possible. There is something peaceful in that constancy. While so much in life is uncertain and changing, these passages remain. They were built with care, through difficulty, by people who knew they were creating something lasting. Their work persists. The tunnels they carved remain, serving purposes those builders could not have fully imagined, adapting to new uses while maintaining their essential function of connection. If there is a lesson in all of this, perhaps it is about the value of work that serves beyond ourselves. The tunnel builders rarely know everyone who will benefit from their labor. They work knowing that their effort will matter, trusting that connection has inherent worth. That trust, that willingness to work for purposes larger than immediate reward, is what makes civilization possible. It is what allows one generation to leave gifts for the next in the form of infrastructure that enables flourishing. You need not carry these thoughts heavily. Let them be light, like the understanding that somewhere beneath the surface, careful work continues. Machines hum in darkness, removing stone grain by grain. Engineers study data, making minute adjustments to maintain alignment. Crews inspect joints and seals, ensuring that water stays where it belongs. This work, this care, this attention happens constantly, invisibly, making possible the visible world above. Your role in this story is simply to appreciate, perhaps, that such work exists. To notice occasionally that when you descend stairs into a subway station, you are entering a space that once did not exist, that was carved carefully through earth, that represents countless hours of effort by people you will never meet. That recognition, quiet and brief, is its own kind of connection, linking you to the chain of human effort that makes daily life possible. As you release attention to these details, notice your breathing has slowed. Notice that your body has settled more deeply into comfort. Notice that thoughts are becoming less distinct, less urgent, drifting like debris floating in a slow underground stream. This is exactly right. There is nothing more you need to understand about tunnels tonight. The knowledge you have gained can rest with you, surfacing when relevant, remaining quiet otherwise. The world beneath cities will continue its hidden existence. Water will flow through aqueducts. Trains will glide through transit tunnels. Utilities will hum in their passages. All of this happens without needing your consciousness, which is free now to release attention and drift into rest. The work continues. You can let go. Somewhere far below, in total darkness, a tunnel waits patiently. It has no sense of time passing. It simply exists, ready, available, serving whenever called upon. In this readiness, this patient availability, there is something like peace. The tunnel does not rush or worry. It is what it is, doing what it was made to do, no more and no less. You can borrow that quality now. Simply be. Simply rest. Simply allow yourself to drift into the quiet darkness that leads to sleep. There are no more facts to learn tonight. No more wonders to consider. Just the gentle release into rest, into darkness, into the peace of letting go. Thank you for exploring these hidden passages with me tonight. Thank you for your curiosity, your attention, and your willingness to consider the unseen infrastructure that shapes our world. Wherever you are, whatever lies above or below you, may you rest well knowing that beneath the surface, careful work continues. The tunnels will be there tomorrow. The cities they serve will wake and move and live. But tonight, that can all proceed without you. Your only task now is rest. Good night, sleepy explorer. Safe travels through your own inner darkness, where dreams tunnel through consciousness, connecting thought to thought in passages no one else will ever see. May your rest be deep and undisturbed, like the ancient stone that surrounds the deepest tunnels, holding firm, unchanging, patient as the earth itself. Good night.